In this video, we solve problems with the product rule and quotient rule in calculus, but we avoid the chain rule. That comes in the next video. Problem 1, part A, says to find the derivative of this exponential growth function, f of x equals e to the 2x power. We're not allowing ourselves to use the chain rule. That's certainly the quicker way to go. Here we want to use the product rule, and the key is to realize you can write this as a product. You can think of 2x as x plus x, and then by a property of exponents, that's the same as e to the x times e to the x. It is the product of two functions, two basic exponential functions. The derivative of e to the x we know is e to the x. But what is the product rule in general? Let's go ahead and write it down before we solve part A. It says that the derivative of a product of two differentiable functions, meaning they have derivatives, is the derivative of the first function, which I'm calling f of x. Its derivative is f prime of x times the second function plus the first function times the derivative of the second. It is not the product f prime of x times g prime of x. That is what people often think it should be. That's in fact what I think Newton thought it should be at first. But no, this is how you differentiate the product of two functions. So coming back to part A, we want to differentiate e to the 2x, which is e to the x times e to the x. We can use the product rule here. Don't be confused by the fact that here the function is called f of x times g of x, and here f of x, I'm not writing it as a product initially, but I could think of this as being a g of x and an h of x, say, and go ahead and use the product rule in the form that you see here. It's more helpful, however, to think internally in your mind. I need to differentiate the first function, then multiply times the second. Well, the derivative of e to the x is e to the x, so I get e to the x for the derivative of the first function, times the second, that's another e to the x, plus the first function, e to the x, times the derivative of the second function, e to the x. A bunch of e to the x's here. These combine to give e to the 2x plus e to the 2x, and that is the same as 2e to the 2x, and that is the answer for the derivative of e to the 2x. Again, if you know the chain rule, it's much quicker. You can get this answer more quickly, but that comes in the next video. Part B, find the derivative of f of x equals e to the negative x power. Can we do something with the product rule here? Well, we want to use the quotient rule, actually. E to the negative x power is the same as the quotient, 1 divided by e to the x power. What does the quotient rule say in general? It's even a little trickier than the product rule. It tells you how to differentiate, find the derivative with respect to x, of a quotient, meaning a fraction, f of x divided by g of x. I remember it this way. I say low d high minus high d low over the square of what's below. What in the world did I just say? Low means the lower function, g of x. D high means, well, times, d means derivative, times the derivative of the high function, f prime of x. Low d high, again, d meaning derivative, minus high, f of x. D low, d meaning derivative, means derivative of g of x, the lower function, over the square of what's below, meaning over g of x quantity squared. Low d high minus high d low over the square of what's below or below. Okay, that is the quotient rule that right there. You can see it's complicated. The most common mistake people make here is they switch around the order of what's in the numerator. It matters the order. Start with the low d high minus high d low. It didn't matter with the product rule because with addition is commutative here, and so you can switch those around. Subtraction is not commutative. So that's the rule that we need to use. Amazingly, it's pretty complicated. We want to use it for this function, 1 over e to the x. The high function then is 1, the constant function 1, and the low function is e to the x. So to differentiate, f of x is e to the negative x, which is 1 over e to the x. To differentiate that with the quotient rule, we get low e to the x. D high means the derivative of the top. That's 0. The derivative of 1 is 0. Minus high, that's 1. D low, the derivative of e to the x is e to the x. Over the square of what's below, e to the x quantity squared. We can simplify this. This becomes a 0. This becomes a minus e to the x. And here I can multiply those exponents and get e to the 2x if I like. And then this can be simplified a little bit. I can subtract exponents. I could write negative e to the x minus 2x, and that's the same as negative e to the negative x, and that is the answer. Once again, if you know and allow yourself to use the chain rule, it's much, much quicker. But that takes practice. Again, that comes in the next video. Part C. Find the derivative of this product. F of x equals the product of this binomial expression, x cubed plus x times square root of x, times the exponential function 4 to the x, where the base now is not e, it's 4, and so we need a logarithm will come into play. But more fundamentally, I need the product rule because that is the product of two functions, the first function and a second function. Can you use the distributive property instead and distribute the 4 to the x through? Yes, you could, but you'd still need the product rule. And in fact, if you do it that way, you need the product rule twice. So we're going to avoid that. It's also going to be helpful to realize that x times the square root of x is the same as x to the first power times x to the 1/2 power. And if you add those exponents, you'll get x to the 3/2 power. And that will be helpful for differentiating that with the power rule. So go ahead and take the derivative. I'll just write f prime of x right away, but maybe you want to write this down first since you can't see it on the screen. Again, x cubed plus x to the 3/2 in parentheses, all times 4 to the x. The derivative of the first, I need also linearity. The derivative of a sum is the sum of the derivatives. The derivative of x cubed is 3x squared. Don't forget parentheses here. The derivative of x to the 3/2 power is 3/2 x to the 1/2 power. I'm using the power rule there. That's the derivative of the first times the second, plus the first function, x cubed plus x times square root of x, which is the same as x to the 3/2 power, times the derivative of the second. The derivative of 4 to the x is natural log of 4 times 4 to the x. Okay, so this complicated expression, which could be simplified a little bit perhaps by factoring the 4 to the x out, is the derivative of that function. Wow. All right, these rules are pretty amazing. Imagine doing these things with the limit definition of the derivative. I would not want to do that. But with these rules, we can find these derivatives. Part D, find the derivative of this function right there. It's a quotient. We're going to need the quotient rule. X cubed plus 5x plus 3 is the top, the high function, and x squared times e to the x is the bottom or low function. We need the quotient rule there. I'll just write f prime of x again right away. Remember, it's low d high minus high d low over the square of what's below. Low is x squared e to the x. Write that first. X squared e to the x. D high means I need to take the derivative of the top function. It's a polynomial with more than one term. I'm going to need parentheses. Careful with parentheses. The derivative of that is going to be 2x plus 5. Put it inside parentheses. 2x plus 5. That's essential to have parentheses there. You're multiplying this product times this entire thing. Low d high minus high d low. So here we have high is x squared plus 5x plus 3. D low, this gets complicated. To take the derivative of x squared times e to the x, I need the product rule. I need the product rule within the quotient rule here. Okay, so it can get really tricky, but again, it's amazing that all this works. So take the derivative of x squared times e to the x. The first function is x squared. Its derivative is 2 times x, times the second function. I'm using the product rule here. Plus the first function x squared times the derivative of the second. The derivative of e to the x is e to the x. Over the square of what's below, so it's x squared e to the x all squared, which of course I could also write as x to the 4th times e to the 2x. But I'll just go ahead and stop right there. By the way, when I quiz my students on gateway exams related to all this, I tell them not to bother simplifying this. Okay, because you're gonna make mistakes if you try to simplify it too fast. So just leave it as is, though parentheses are absolutely necessary in appropriate spots. Okay, it's something to be very careful of. All right, part E. Assuming f and g are all differentiable for all x, meaning they have derivatives, find the derivative of this function. Of course, we'd also have to be avoiding where we're dividing by 0 there possibly, but I didn't bother stating that here. So j of x is a quotient, most fundamentally, f of x times g of x, all divided by h of x. But when we differentiate the top, the high, we will also have to use the product rule. So the derivative of j, I'll go ahead and write the f, g, and h in here as well, is d dx of f of x times g of x, all divided by h of x. Low d high minus high d low over the square of what's below. Low d high means the derivative of f of x times g of x, for which I need the product rule as well. So inside the parentheses, I'll also do the derivative of the first function times the second function plus the first function times the derivative of the second function. So we got low d high minus high f of x times g of x. D low means the derivative of h, right, h prime of x, over the square of what's below, h of x quantity squared. So an abstract situation here, but you definitely can do it. In the second problem, we want to get practice again, either with a product rule or quotient rule, but we also want to remind ourselves what derivatives mean. They give us equations of tangent lines, they tell us where the function is increasing or decreasing, and the second derivative will also tell us where the graph of the function is concave up or concave down. So the function is 2 times x times e to the negative x, which, as we saw in problem 1, could also be written as a quotient 2x over e to the x. And what this ultimately means is we could certainly use the quotient rule, or since we already know from number 1 the derivative of e to the negative x, it was negative e to the negative x, we saw that in number 1, we could get away with the product rule if we allow ourselves to use the result of number 1. So let's go ahead and find f prime of x. I think what I'll do is I'll use the quotient rule here for finding the first derivative, and I'll confirm that we get the same answer if we use the answer for number 1. But then when we find the second derivative, we'll use that fact once again that the derivative of e to the negative x is negative e to the negative x. So let's use the quotient rule here. The high function is 2x, the low function is e to the x. Low d high, you can never really get enough practice with the quotient rule. Low d high minus high d low, the derivative of e to the x is e to the x, over the square of what's below. This can be simplified. We can factor out an e to the x out of the top and also a 2 if we like. 2 e to the x times in parentheses 1 minus x, it looks like, all over e to the x quantity squared. I could multiply those exponents, but I can also just cancel one of the e to the x's like that. And we get 2 times 1 minus x over e to the x, which can also be written as 2 times 1 minus x times e to the negative x. Okay, so that would be the derivative. And let's confirm that we get the same answer if we had used the product rule and the fact, again, that the derivative of e to the negative x is negative e to the negative x. And we'll check the answer that way. F prime of x, thinking about the product rule, there's the first function, there's the second function. The derivative of the first function is 2 times the second function plus the first function, 2x, times the derivative of the second, e to the negative x. Again, here's where we're using the fact that the derivative of e to the negative x is negative e to the negative x. And then we can factor out a 2e to the negative x. And what we're left with is a 1 there and a minus x there. We do get the exact same answer. We checked it. Okay? Let's now find the second derivative. And for that one, we'll use the fact, like we did with the checking, that the derivative of e to the negative x is negative e to the negative x, because now we're going to differentiate this. The second derivative of f is the first derivative of f prime. Now your first function is 2 times 1 minus x, or if you prefer, 2 minus 2x. Think of that as being the first function in parentheses. And your second function is e to the negative x. So the derivative of the first function, 2 minus 2x, is negative 2. And the second function is, again, just e to the negative x, plus the first function, 2 minus 2x, times the derivative of the second function. Once again, the derivative of e to the negative x is negative e to the negative x. You got to be careful about your minus signs here. Real easy to make a mistake. Let's go ahead and distribute this through. Well, okay, maybe I should factor out an e to the negative x first here. So I get e to the negative x out in front. This one will be left with a negative 2. This one will be left with this, with the minus sign multiplied through, so that'll be plus 2x minus 2. So if I've not made a mistake, it looks like I can, let's see, e to the negative x, This simplifies to 2x minus 4 if I like. That's fine. I could also factor out a 2. I could write this 2e to the negative x, and then in parentheses x minus 2. Okay, either way is okay. And again, for gateway tests, that's fine to leave it like that. Okay, so we found the first and second derivatives. We did part A. On to part B. Find an equation of the tangent line to the graph of f at x equals 0. The general equation of a tangent line at x equals a. You could give the tangent line function a name if you like L of x for linear is f of a plus f prime of a times x minus a. What's a? A is the value of x that you happen to be thinking about. That is the a right there, 0 for this example. So this is going to be f of 0 plus f prime of 0 times x minus 0. F of 0 is 0. There's f of x, plug in 0, you get 0. F prime of 0 is not 0. Plug in x equals 0 here, you get 2 times 1 times e to the 0 is 1. 2 times 1 times 1 is 2. So this becomes 0 plus 2 times x, or just 2x. The equation of the tangent line is y equals 2x. It's a straight line through the origin with a slope of 2. Pretty simple. Part C. For what intervals is the graph of f decreasing? Or you could say, is f a decreasing function? Would be actually a more common way to ask that question. All right, we know the derivative tells us where the function is increasing or decreasing. If it's a differentiable function, like this is, we got to focus on this and see where it's positive or negative. Since we're after where f is decreasing, we need to think about where that's negative. So let's go ahead and write it down here. So again, the first derivative of f, let's write it in factored form, is 2 times in parentheses 1 minus x times e to the negative x. We want to essentially solve this inequality. Solve for x. What values of x, what interval values of x will solve this inequality? Well, this is the product of 3 things. 2, which is positive, 1 minus x, which could be positive or negative, and e to the negative x, careful, e to the negative x is always positive, no matter what real number x is. This is always a positive number. So the sign of this product is completely determined by the sign of 1 minus x, because 2 is positive and e to the negative x is positive. This is equivalent to saying 1 minus x is less than 0. And that, if you add x to both sides, is equivalent to saying 1 is less than x, or if you prefer, x is greater than 1. Those are equivalent inequalities. So that is the answer. That's the interval for which f is decreasing when x is greater than 1. Now, maybe your teacher is fine leaving the answer like this. You might also write the answer in interval notation. The open interval from 1 to infinity is another way to write the answer. And you also might be told to write the answer in what's called set builder notation, the set or collection of all numbers x, all real numbers, this fancy looking r means real, with the property that x is bigger than 1. It would be kind of a fancy set builder way of writing this notation. Maybe you also want to graph the set. Here's 1. Make an open circle there because when 1's not included, all the numbers to the right of 1 on the number line are where this function f is decreasing, and you could check with your calculator. The graph would be decreasing there, and evidently increasing when x is less than 1. So the graph is going to be going up, reach evidently some sort of maximum at 1 before decreasing again. I'll let you think about that a little bit more or graph it with your calculator. Part D. On what intervals is the graph of f concave up, where the second derivative is positive? It'll be concave down where the second derivative is negative. So let's write down the second derivative that we found in factored form. F double prime of x, it's right here, is 2 e to the negative x times x minus 2. We want to solve for where f is concave up, so where the second derivative is positive. Once again, product of 3 things. The first 2 things here now are positive no matter what x is, so the sign is completely determined by x minus 2. X minus 2 being positive means x is bigger than 2, or equivalently 2 is less than x. That would be your answer. In interval notation, it would look like this. Set builder notation, it would look like this. The vertical line, by the way, means such that, or with the property that. And on a number line, it would be everything to the right of 2. So put 2 right there, say, with an open circle, everything to the right of 2. Now, what does the graph of this function look like? I could certainly graph it on my calculator, but I think I can do a quick graph without my calculator. It looks like this, and its value at 0, remember, was 0. It's actually negative when x is less than 0, but still increasing when x is between 0 and 1. And it's concave down over there. And then once you reach 2, then it becomes concave up and approaches the x-axis as a horizontal asymptote. There's a local maximum, in fact, a global maximum at x equals 1. What would the value there be? It would be 2 times 1 times e to the negative 1, which is 2 over e, is the maximum value. And there's what's called an inflection point at x equals 2, where the graph changes concavity from concave down to concave up. Calculus is useful for sketching graphs. Number 3 is kind of a strange and tricky problem, but it's actually very important. Part A says find a possible formula for a function f whose derivative is given. And it's kind of a complicated derivative. F prime of x equals 5x to the 4th times e to the x plus x to the 5th times e to the x. We are here trying to find something called an antiderivative, or antiderivative if you prefer, of this function f prime of x. We are undoing the differentiation. In general, this can be very tricky, if not impossible. In this case, even though this function f prime of x is kind of complicated looking, it should feel very familiar based on what we've done so far in this video. This should look like something that we get with the product rule. Yeah, and 5x to the 4th, that is the derivative of x to the 5th, and the derivative of e to the x is e to the x. You can guess the answer if you're careful about it. That could be the derivative of the first function times the second function plus the first function times the derivative of the second. Yeah, that's got to be right. This is the derivative of x to the 5th times e to the x. Check it in your mind. Differentiate the first function, x to the 5th, you'll get 5x to the 4th times the second function plus the first function times the derivative of the second. This does work. It's actually not the only answer. It says find a possible formula. There's actually infinitely many answers. How can that be? Well, you can add any constant here. I could write plus c. I could pick a particular c like I initially did, c equals 0. I could pick c to be 1. I could pick c to be 2. I could pick it to be pi. I could pick it to be a million. I could pick it to be negative a billion. Okay, any c works. I will leave the plus c here, but just realize to answer the question, you can pick a particular c like c equals 0. B is similar. Find a possible formula for a function f whose derivative is this. I wrote it like a quotient first. It does happen to equal this. I'll let you think about that. It can be simplified. So we could try to answer the question, evidently, perhaps either by undoing the quotient rule or undoing the product rule. We should get the same answer up to a plus c. Again, guessing can help. The quotient rule, let's think about it that way. Low d high minus high d low over the square of what's below. Low d high, I guess the high must be x to the 5th. Minus high, yeah, d low, the derivative of e to the x is e to the x. Over the square of what's below. E to the x quantity squared is the same as e to the 2x. Yeah, f of x equals x to the 5th over e to the x will work. Low d high, minus high d low over the square of what's below works. This does check. This is the same as x to the 5th times e to the negative x, and if you use the product rule, plus the fact that the derivative of e to the negative x is negative e to the negative x, like we've seen, you'll get this expression here. And once again, I can add a plus c, where c can be any constant. Our last couple problems are going to be word problems that are kind of tricky when you look at this, and tricky to think about, but I think very important here. The quantity Q of skateboards sold, skateboards, it could be something else, depends on the selling price P in dollars. Think about this economically. As the price goes up, you're going to sell fewer skateboards in any given amount of time, maybe a month or something. So Q is a function of P. In fact, it would be a decreasing function of P. As P gets bigger, Q is going to get smaller. You were given that f of 150 is 15,000. In other words, think about, we're going to answer part A and part here. What does this tell you about sales of skateboards? I'm just going to answer it verbally and not bother writing it down. This is going to say when P is 150, when the skateboard is $150, you're going to sell 15,000 of them, again in some unspecified amount of time, like a month. And the derivative at 150 is negative 120. When the price of each skateboard is $150, the rate of change, the derivative is the rate of change of skateboard sales, the QDP with respect to price, is negative 120. That's probably worth writing down. Okay, well, okay, maybe I should write these both down. Let's go ahead and do it. When the price, we're thinking about interpreting what these things tell you about sales of skateboards. When the price is $150, you could say per skateboard, but I won't bother at the moment. You will sell 15,000 of them, 15,000 skateboards. Again, maybe in a month. That's what the function value tells you. What about the derivative value? It's very important to, once again, say when the price is $150, because the input for the derivative here is 150. When you plug in other inputs, you get a different derivative. When the price is $150, the rate of change, derivatives are rates of change. You could even say instantaneous rate of change of Q with respect to P. Skateboards sold. Skateboards, can I spell skateboard? Skateboards sold with respect to price, I'll abbreviate with respect to like that, is negative 120 skateboards per dollar. Skateboards per dollar. That's telling you the rate of change. The units are going to be units of the dependent variable per unit of the independent variable. I won't write it down. This time I really won't, but let me say it verbally. This means, we might write it down when we think about what happens here for this part C, but not in part A. This means that if you raise the price by, say, $1 to 151, yeah, we'll think about that in part C, you'll sell fewer skateboards because it's negative. The rate of change is negative. How many fewer? About 120. It's an estimate. It's maybe not a perfect estimate, but it's an estimate based on past data, perhaps, or based on a reasonable formula for f of p, which we're not given. That's okay. Part B, the total revenue R earned by the sales of skateboards is P times Q. Does that make sense? Revenue is money that you take in. It's not the same as profit because you're not considering expenses. P times Q. P is the price, dollars, and Q is the quantity sold, skateboards. In fact, it's probably better to think of the units of P here as dollars per skateboard times number of skateboards. The skateboard units would cancel, leaving you with dollars. This is an amount of money. It says find dRdP at P equals 150. This line means evaluated at P equals 150. This is the Leibniz notation for the derivative. It's very tempting to look at this equation and say, oh, I guess the answer is Q. But wait a minute. Q is not a number. It's a variable. Q depends on P. It's very important here to realize you're differentiating with respect to P, but Q depends on P. Q is f of P. So I need the product rule. This is the trickiest part of this question right here, is to realize that. And now this is the product of two functions. The first function is P, the second function is f of P. So by the product rule, dr dP is the derivative of the first, 1, times the second, plus the first times the derivative of the second. Interesting. F of P plus P times F prime of P. That is how the revenue differentiates with respect to price. Now plug in the numbers. We're evaluating dRdP at p equals 150. We get, looking at this is f of 150 plus f prime, 150 times f prime of 150. Plugging the given numbers in, f of 150 is 15,000, f prime of 150 is negative 120. This becomes 15,000 plus 150 times negative 120. What does that simplify to? 15,000 minus 150 times 120 is 18,000, so we're subtracting 18,000. We get a negative answer, negative 3,000. What are the units going to be? Units of revenue are dollars. Units of P are also dollars. You might say dollars per dollar per skateboard. Yeah, P is the price. Probably better to think of this as dollars per skateboard. Now, technically speaking, you could cancel the dollars and write this as units of skateboards, but it's better not to, because it's going to help us interpret it in part C. Part C, first part says, what is the sign of this derivative? Well, it's negative. If skateboards are currently selling for 150, what happens to the revenue if it's increased by $1 to $151? The fact that this is negative means the revenue's got to go down. But wait a minute, how can that be? You raise the price. You're going to sell fewer skateboards, and the increased price per skateboard is not enough to offset the fewer skateboards sold. If the revenue is increased to $151, what would we estimate, if the price is increased to $151, what would we estimate be the new revenue? Or what could we describe here? We could describe it this way. If the price is increased from 150, let's go ahead and write dollars per skateboard, to $151 per skateboard, the revenue will decrease by about, this is a linear approximation, about $3,000. The change in revenue, delta R, is approximately that rate of change of revenue with respect to price, evaluated at P equals 150, times the change in price. This is negative $3,000 per dollar per skateboard, and this is $1 per skateboard, giving us negative 3,000 for the change in revenue, dollars. You can also say decrease by 3,000. Is this really what's going on? Approximately, okay? Let's think about the revenue and this problem by thinking about the revenue when the price is $150 per skateboard. It's P times Q. P is 150. Q is 15,000. 150 times 15,000, which is 2.25 million, is your revenue in dollars when the price is $150 per skateboard. If we increase the price to $151 per skateboard, we sell fewer skateboards. By about how many? About 120 fewer. That was part A. So instead of selling 15,000 skateboards, we're going to sell 14,880, approximately. Does the revenue go up or down? It should go down by about 3,000. Yeah, take that number and subtract the starting revenue. Make sure I get the right number of zeros. It went down by about changed by about negative $3,000. To be more precise, negative 3,120. But the linear approximation on a relative scale at least, is pretty close. It's also important to think about units in this last problem. And in this problem, when it says explain something, I really am just going to explain it verbally sometimes and not write it down to save some time here. F of V is the gas consumption in liters per kilometer. Okay, that's a little bit differently than we usually think of gas consumption. Usually you'd think of it in miles per gallon or maybe kilometers per liter, but this is a little different. Of a car going at speed V in kilometers per hour. So this tells you how many liters of gas the car uses to go 1 kilometer. You know, it wouldn't be many. You wouldn't use many liters of gas to go 1 kilometer. You are told that f of 80 equals 0.0625 and f prime of 80 equals 0.0025. When you've got the cruise control set to 80 kilometers per hour, you use 0.0625 liters of gas to go 1 kilometer. I did pick this 0.0625 kind of special. 1 over 0.0625 is a nice number. It's 16, ultimately meaning you go 16 kilometers on 1 liter. It's another way to think about the gas consumption, in fact, a more common way to think about it. The rate of change, the derivative, when you set the cruise control to 80 kilometers per hour, is 0.0025. That's the rate of change of gas consumption with respect to speed. Its units would be liters per kilometer per hour. So if you increase the speed a little bit, f of v in liters per kilometer will go up a little bit. You'll use a little bit more gas to go 1 kilometer. That's actually worse gas mileage. Okay? This is confusing but important. All right, part A. Let g of v be the distance the same car goes on 1 liter of gas at speed v. What is the relationship between f of v and g of v? Find g of 80 and find g prime of 80. G of v is the more common way to think about gas mileage. In this case, in terms of kilometers per liter. The units of g are distance per unit of gas, volume of gas, liters. So it's the reciprocal of f of v. G of v is 1 over f of v. Oh, we're going to use the quotient rule here to differentiate this. We need to find, that's the relationship. We need to find g of 80 and g prime of 80. G of 80 is 1 over f of 80. 1 over 0.0625, and I did that already. That's 16. 16, and the units would be the reciprocal of these units, kilometers per liter, a more common way to think about gas mileage. What about the derivative? What about g prime of 80 ultimately? We need the quotient rule to differentiate this. Low d high minus high d low over the square of what's below, and that simplifies to negative f prime of v over f of v quantity squared. Plug in v equals 80. You get negative f prime of 80 all divided by f of 80 squared. That's negative what? F prime of 80 is 0.0025. F of 80 we've seen is 0.0625. That needs to be squared. Ultimately, this is the same as multiplying by 16 squared when you divide by 0.0625 squared, but I'll type it in as it is. Negative 0.0025 divided by 0.0625 squared. Probably should have kept that inside the parentheses. Negative 0.64 if I've not made a mistake. Let me just double check that 16 squared, which is 256, times negative 0.0025 is the same thing. Yeah, now add the negative sign. So this is negative 0.64. This looks correct here. What would the units of this be? And in C, we're going to ultimately explain the practical meaning of these functions and their derivatives. Let's go ahead and do part C here verbally right now. This is the rate of change of the function g of v with respect to changing the speed v itself. The units of g of v are in kilometers per liter. This is kilometers per liter per kilometer per hour. Again, you could cancel the kilometers and you could write the units here ultimately as hours per liter, but it's more beneficial to think about it this way because you're thinking about how does the values of G of V get affected if I increase the speed a little bit by like 1 kilometer per hour. If I increase the speed a little bit from 80 kilometers per hour to 81, I would expect the value of G of V to go down by about negative 0.64 from 16 to about 15.46 or 36. That's probably too many significant digits. It's going to go down. This mileage, you might say, or kilometerage, I've never used that word before, is better when it's bigger. If you can go more kilometers on 1 liter, that's better. The fact that this is negative means it's going to go down if you increase your speed a little bit. That's worse. You're getting worse mileage. Okay? That's the practical meaning. Part B, let H of V be the gas consumption in liters per hour. So you're traveling at speed V. You could do liters per kilometer, thinking of how much gas do you use to go 1 kilometer. Here we're thinking about how much gas do we use to go when we're traveling for 1 hour, ultimately. So this is in liters per hour. All right, so what's the formula for H of V? How is it related to F of V? Units. Think about units. We want this to be in liters per hour. We know F of V is in liters per kilometer. The liters is in the numerator, but the kilometers is in the denominator instead of hours. How could I get the units to cancel appropriately to give me ultimately liters per hour? I need something a quantity that has units of kilometers per hour. Hey, that's the speed. This is V times F of V. This is in kilometers per hour. F of V is in liters per kilometer. The kilometers cancel, leaving you with liters per hour. So that's the relationship between H of V and F of V. And it implies that H of 80 is 80 times F of 80. So that'll be 80 times F of 80 was 0.0625. 80 times 0.0625 is 5. What are the units? Liters per hour. So when you are traveling at 80 kilometers per hour, using 0.0625, 1/16th of a liter for every, let's see, this was 0.0625. This is 1/16th of a liter for every kilometer you go. You're going to use 5 liters per hour because you're ultimately going to go 80 kilometers. All right? In that 1 hour. How about the derivative? Use the product rule. The derivative of V is 1 times the second function plus the first function times the derivative of the second. Plug in 80, you get F of 80 plus 80 times F prime of 80. F of 80 was 0.0625. F prime of 80 is 0.0025. This is going to be a positive number. 80 times 0.0025 is 0.2 plus 0.0625 gives 0.2625. What would the units be? The units of H of V are liters per hour. We're differentiating with respect to V, the speed. This is going to be liters per hour per kilometer per hour. So what does this mean? What's the practical meaning? It's positive, and about 0.26. If we increase our speed a little bit from about 80 kilometers per hour to 81, and again, we're using cruise control, we would expect H of V, a measure of fuel consumption in liters per hour, to go up a little bit. You're going to use more liters for every hour, okay? That's worse. That going up means you're using more gas for every hour. Thanks for watching.